Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. I'm Dr. Shahid Amin, and today I'm going to start the lecture series on organic chemistry. And the first lecture, this is from the course Introduction to Organic Chemistry that is approved by Higher Education Commission of Pakistan, and the course title is Chem 161. Today's lecture will contain a discussion on electronic structure of atom, that how the electrons are distributed within an atom. So let's start our lecture. Structure of atom. We know that atom is the building block of matter, and atom consists of two major parts. One is very small nucleus that contains most of its all of its positive charge along with some neutral particles, and around this nucleus there is a very large space where negatively charged particles, these are moving, they are called as electrons. So the nucleus, as I said before, this is a very small particle as compared to total size of atom, and the diameter of this nucleus, this ranges from 10 raised to the power minus 14 to 10 raised to the power minus 15 meters. Whereas if we look at the space that is occupied outside the nucleus by revolving electrons, this is its diameter is approximately 10 to the power minus 10 meters. So we can imagine how small nucleus is as compared to the total size of atom. Although electrons are revolving around the nucleus and they are occupying most of the space, but it doesn't mean that the size of the electron or the total density of electron, when we consider the wave nature of electrons, this is electron is somewhat of very large size as compared to the nucleus. This is actually most of the space within the atom is empty. So the nucleus, very small particle that is present in the middle of the atom, serving as the center of the atom, and around this nucleus there are revolving negatively charged electrons. So now we look at how are the electrons distributed inside the atom. Electrons actually revolve around the nucleus, and their revolution defines the probability of finding them in various regions of space as compared to the nucleus. And these regions are called as shells or orbits. You can see this is the nucleus, and around the nucleus there are some specific paths where electrons are revolving around this nucleus. So the energy of electrons within these shells, this is quantized. Quantized means they have a specific amount of energy while they are within a specific path. And this energy is quantized, that is, this is a specific amount, and there is no continuum of energy when electrons are considered with respect to their orbits. So it means that, for example, if we take these two orbits or shells, this is, for example, the first shell inside a carbon atom, and this is the second shell. The energy of electron within this first shell, this has a specific value as compared to the energy that is of electron present in the second shell in this atom. So the shells occur only at quantized energies, in which three important effects actually counterbalance each other. So these effects are the electrostatic attraction between this nucleus and these electrons. So this electrostatic attraction actually tends to draw this electron too much near to this nucleus. So if it happens, what will be the result? The atom will just break down, but it never happens. Rather, electron continuously moves around this nucleus because of its kinetic energy. So the electrostatic repulsion between the electrons that are, for example, inside the same orbit, or they are in the nearby orbits, this electrostatic repulsion, this is also overcome because of the quantization of energy, that is electrons are present at some specific distances. Then we look at if we look at the wave nature of electron, that prefers to be delocalized, thereby spreading the electron density away from the nuclei. Delocalization means the spreading of electron density over a large volume of space inside this atom. Now the electronic shells, for example, these orbits, number 1, number 2, number 3, and so on, these are identified by the principal quantum numbers. Principal quantum numbers are designated by natural numbers 1, 2, 3, and 4. And within each principal quantum number, the total number of electrons, this is defined by this number, 2n square, where this n is the number of the shell. So it means if we are talking about the first shell, how many total electrons will be there? N raised to power 2, that is 1 raised to the power 2, that will be 1 multiplied by 2, it will be only 2 electrons. Similarly, for the second shell, the total number of electrons that will be there, this will be 2 multiplied by 2 raised to the power 2. So it means this becomes equal to 8. So total number of electrons that could be accommodated within the second shell, this is 8. Similarly, the third shell, it becomes 18. For fourth shell, it becomes 32, and so on. Now we look at the wave nature of electron and quantum mechanics. Actually, although electron is normally considered as a particle, but in fact, electron has a wave nature also. So the wave nature of electron, this is studied by a specific branch of physics that is called as quantum mechanics or wave mechanics. The beginning of this new approach was provided by Max Planck in 1900, postulating that the light consisted of photons, that are the packets of energy, of electromagnetic radiations, and the energy of photon is proportional to the frequency of light, that is given by this equation. In 1923, de Broglie advanced the revolutionary idea that if light exhibits properties of particle, that is the photons that are in motion, then particles in motion like electrons, they should exhibit the properties of a wave. And this is given by his well-known equation that is called as the de Broglie equation. After about 3 years, in 1926, Erwin Schrödinger, he proposed an equation that describes the wave properties associated with an electron inside an atom or a molecule. And these wave properties are explained by this equation, not simple, sorry, this equation that is called as the Schrödinger wave equation. This equation actually was derived by considering the wave nature of this electron. For example, this is a hydrogen atom, and this is the electron inside this hydrogen atom revolving the nucleus. So by considering the wave nature of this electron, the equation derived by Schrödinger, this is given here. Now, by the solution of this Schrödinger wave equation, we come to know about some specific regions within the atom where, considering the wave properties of electron, the probability of finding the electron, it becomes somewhat very high. And these regions, these are called as the atomic orbitals. So when Schrödinger wave equation is solved, its solutions give some actually some sets of solutions are obtained, and these are called as the wave function, and these are denoted by psi, a Greek letter. Each wave function is associated with a unique set of quantum numbers and with a particular atomic or molecular orbital. A wave function occupies three-dimensional space and is called an orbital. which can contain a maximum of 2 electrons. These orbitals are also called as the subshells. The value of psi square is proportional to the probability of finding an electron at a given point in space, or the electron density. So, where psi is the wave function, psi square is the electron density. When we plot electron density in a given orbit, theoretically reaches to, and this plot theoretically reaches to infinity but becomes vanishingly small at longer distances from the nucleus, and this could be shown in this as this figure. For example, this is the nucleus. Starting from the nucleus, there is no electron density. After some distance, somewhat electron density appears. It becomes deepened, more deepened, and then it fades out until we reach a region where the electron density again becomes zero. So with the increasing distance, gradually the electron density becomes zero. Now it's important to be noted that the value of psi at any point can be positive or negative. So wave function at some specific point may be positive or negative. But the value of psi square, that is the probability of finding electron, this is the real one. This will always be positive in an orbital. Now, within an atom, the region where the value of psi square becomes zero is called a node. For example, if we consider this picture, this region where there is no electron density, this is called as a node. This is one shell or orbital, and this is the second orbital. Orbitals, also called subshells, are considered the part of the atomic orbits or shells and are designated as S, P, D, and F. The number of the types of orbitals within an orbit or shell depends upon its principal quantum number. For example, if n is equal to 1, that is the first shell, this contains only one type of orbitals, and this orbital is s orbital. If n is equal to 2, that is the second shell, then there are two types of orbitals, s and p. With n equal to 3, three types of, sorry, here is a mistake, three types of orbitals, s, p, and d are present. So if n is equal to 4, then four types of orbitals are present, that are s, p, d, and f orbitals. Now, if we look at the shapes of these orbitals, that is the shape of the electron density around the nucleus, s orbitals have the shapes of spheres, and the p orbitals, they have shape of dumbbells, like shown here. Here, these orbitals are the graphics that are obtained by solution of Schrödinger wave equation and then plotting the wave function in the space. Then these orbitals are obtained. Similarly for p, these are the orbitals. These different colors, actually, these show the different phases of two regions of these orbitals. One is positive, the other one negative. Similarly, all of these, and these are the three p orbitals. We talk about these now. Now this p orbital has three orthogonal angular momentum states in three-dimensional space. That is, there are three independent degenerate p orbitals at 90-degree angles between them, and these are directing along the x, y, and z axis designated as px, py, and pz. These orbitals are different only on the basis of their orientation in space. Otherwise, they have the same energy values. So that's why these are called as the degenerate orbital. Degenerate orbital mean orbitals having same energy. So the upper diagrams that are with some meshwork, these are obtained by plotting the wave function in space by obtained from the solution of Schrodinger wave equation, whereas the lower diagrams, these are actually the graphical representation that we normally use while explaining the chemical reactions or the structure of the atoms and molecules. For organic chemistry purpose, we mostly deal only with these s and p orbitals. So we will not discuss further orbitals like d orbitals and f orbitals in this series of lectures. Here we can see the hydrogen atom first orbital, and this is the cross section of the same orbital. In the center we can see this is nucleus, then there is 0 electron density, and then we have some electron density here that fades out, and until we reach a region where there is no electron density. So now we talk about wave and particle nature of electron for organic chemistry. That is, what's the importance of considering the wave nature of electron or the particle nature of electron while we are studying organic chemistry. Actually, the wave-like properties of electrons, these are the best thing to consider for most aspects of organic chemistry while we are discussing, for example, the structures of organic molecules and the similarly the chemical reactions. So we will be considering these wave-like properties and the electron. We will be talking about these structures and chemical reactions in terms of electron densities rather than the particle nature of electron. And as we said before, S and P orbitals, these are the two most important orbitals while we are discussing organic chemistry, the structures of molecule as well as the chemical reactions. Orbitals interactions refer to the interactions of waves which may be constructive or destructive, that is, adding or subtracting respectively. When two waves overlap, positive phasing adds, that is, the positive phase of two waves, if they combine together constructively. Similarly, the negative phases, if they combine together, that is, one negative combines with another negative, it will be combining constructively. On the other hand, if a positive and a negative phase, they combine together, they will be combining destructively. It means that constructive combination results into bond formation, whereas destructive combination, it doesn't go towards the formation of bonds. Consideration of the particle nature of electron. Is it important sometimes in organic chemistry or never we use it? The answer is that this particular nature of electron, this is important while we consider the charge on electron, because while we are discussing the chemical reactions or we are discussing the electron density or the polarity of the molecules, then we'll be considering the charges on different parts of molecules. So while discussing that one, then we'll be considering sometimes the particle nature of electron. Negatively charged electrons, actually these are attracted to positively charged nuclei, and among themselves they repel each other. In a molecule, the greater electron density will be shown, or this is present on the more electronegative atoms like oxygen, fluorine, some other halogens, and similarly nitrogen. Now, this showing relative electron density on molecules, that is one part of a molecule contains somewhat more positive charge, the other one, this is having more negative charge. This is important because it allows us to identify sites of chemical reaction. For example, if some electron deficient species is attacking a molecule, then that molecule's negatively charged part, it will be interacting more with that electron deficient species, resulting into formation of some new bonds. During a chemical reaction, an area of relatively high electron density on one molecule reacts with an area of relatively low electron density on another molecule. And it's also to be noted that keeping track of overall molecular electron density distributions using computer graphics, it becomes sometimes very convenient. And throughout these lectures onward, well, we'll be discussing the structure of the organic molecules as well as the chemical reactions of organic substances. We'll be using electrostatic potential maps that actually show the areas of relative high electron density and in red color, and the areas of relatively low electron density in blue color. So today we have discussed about the structure of atom, electronic distribution within atom, and some basic principles of the wave nature of electron. In the next lecture, we will be discussing further the distribution of electrons within orbitals, how the electrons are filled up within the atom, within the shells, and in the subshells. And afterwards, we will be going towards our discussion on how the atoms come together so as to give rise to what we call as the chemical bonds. Thank you so much. See you in the next lecture. Assalamu alaikum warahmatullahi wabarakatuh.